But let's turn back to those egg white proteins. I told you that the albumin played an important role in the protection of the embryo, whereas the yolk serves as the nutrient source for that growing embryo. Let's look at some of those. Here is a list, and I think this is a list reproduced from your text. Eight of the most abundant egg white proteins, ovalbumin being the most abundant at 54%. Okay, so there's a food source, right? Then, and obviously the growing embryo does need protein. But let's skip down to a couple of other molecules here. Ovumcoid, present at 11%, blocks digestive enzymes. So invading organisms that might want to consume the egg as food for itself are inhibited by enzymes like ovumcoid. Lysozyme is an important one, present at only 3.5%, but even at that level, it serves as a very effective antibiotic. So destroying the cell walls of invading bacteria so that they cannot grow and again consume and contaminate the egg. Ovomucin again inhibiting digestive enzymes. Avidin, this is an interesting molecule. Very small concentration, but then again, vitamin B7 is present at very small concentrations. But by sequestering that vitamin, we again inhibit the growth of invading organisms which would need vitamin B7 to grow on their own. So we see that there's a wide variety, this is by no means an exhaustive list, a wide variety of proteins in the egg white, all doing various tasks. Since I've highlighted these, I'm going to mention that I've said here that ovotransferrin and the globulins are mechanically denatured proteins. So we'll talk about denaturation later, but let's just hold it in our mind that these molecules are denatured or unfolded by mechanical stress. Let's think about that as whipping with a whisk, for example, whereas ovalbumin is heat denatured. So it becomes unfolded, and that'll be very important in cooking when we apply heat at the stovetop. In this video, I'm showing you again an unfolded protein polymer. So this is just to give you the sense that we have this long string of amino acids, and at each position in the polymer is a monomer with one of 20 possible side chains. And those side chains, again, we can represent with this simple one-letter code. Now we've taken away those letters and all of that side chain information. This color coding means nothing. But what I'm showing you here is that unfolded chain, now represented as beads on a string, can fold up to form complex structures. Those are the native, biologically relevant folded structures in which the protein does the job that it's designed to do. We see that lots of local structure forms, individual elements of the chain forming up, and then all of those individual elements come together to form this large-scale folded structure. What's really important to remember is that the greasy or hydrophobic amino acid side chains bury themselves or sequester themselves in the core of the protein, as we've said before, hidden away from water. And what we're doing now is drawing back all of those individual side chains as stick models. This in itself still doesn't give you a sense of what the shape of the protein really is. For that we have to draw a space-filling model of the protein, which we'll do in just a moment. But still, you can see very complicated. This is the native state. But now we see coming in slowly this cloud forming. This is the surface of the molecule, a space-filling model, if you will, of the molecule. So we see that it's this big glob. But again, a globular shape, mostly with water-loving atoms and functional groups on the surface, and all of the greasy stuff hidden away in the core. Beautiful. Bye-bye. Okay, back to work. Let's think now about egg yolk contents. And first of all, what does the yolk contain? Well, it's full of low-density lipoproteins. Um, what is a low-density lipoprotein? I talked about how those uh, those phosphoglycerides with a polar head group and non-polar tail groups can form these complicated structures. Well, here we have one such structure in which we have this surface layer of phospholipids, right, with water-loving functional groups facing outward towards the solution, and with an oily core, all of their nonpolar tails pointing inwards. And inside this structure, we have those triglycerides, remember the main storage form of fat, as well as other lipids like cholesterol that are extremely nonpolar. Well, it's a lipoprotein, so it's a protein lipid superstructure, and we see that there are protein molecules that are embedded in this. The idea here is that this structure will allow fats that would otherwise be insoluble in water to be soluble and float through what have you, the yolk, the bloodstream, the cytosol. So what we see here is that this structure allows us to dissolve something that would otherwise be insoluble. Again, taking advantage of that, we'll call it amphipathy, right? Loving both water and nonpolar environments. So among other things, among those proteins, an important components in egg yolks are cholesterol and oleic acid, making up a large percentage of the mass of that lipoprotein. Cholesterol we've seen before. Oleic acid is a so-called omega-9 fatty acid. I'll come back to that in a moment. You've heard this kind of terminology used before, but let's focus on other components first. So lecithin is another component of egg yolk, and let me make a distinction. Lecithin, used one way, describes a certain complex mixture that can be extracted from egg yolks. So it's a general term for something that's not very simple. But lecithin also refers to a particular kind of glycerophospholipid. In any case, lecithin, the glycerophospholipid, is present in high concentrations in egg yolk, and again, really important for the formation of those lipoproteins. In terms of cooking, lecithin is a surfactant, and that means, again, that it can interact with polar and nonpolar surfaces. What this means in terms of cooking is that it can destabilize egg white foams, as we'll see, so keep that in mind. Again, keep those egg yolks out of your egg whites when you're trying to make a nice foam or meringue. Lecithin is also found in the seeds of some plants. Soy, I think, is a good source of lecithin. Some nuts are also very good sources of lecithin. Important if you're a vegetarian, you don't eat egg, but you still need these phospholipids so you can find them. And actually, as a vegetarian cook, not just for the nutrient factor, but as a cook, if you want to substitute for making some other non-animal source surfactants for making emulsions, then you can find it in other sources. So what else do we see? Unsaturated lipids make up a very large proportion of the lipoprotein. Omega-9, as I've already said, and I've drawn a picture of oleic acid here, and omega-3 fatty acids. An example would be alpha-linolenic acid. I haven't drawn you that picture, not so important for our purposes. But what do I want to say about this? So what I've shown you here, what I'm drawn here, this is a fatty acid, a free fatty acid. Remember, it's got a polar head and a nonpolar tail. Well, in the core of the liposome, what we really see is this molecule esterified into a triglyceride. If you don't remember what that is, I'll refer you back to that first lecture. Omega, you might be familiar with alpha and omega, right? The last carbon of the lipid chain, and then omega-9 refers to the 9th carbon inside the chain, and that's where our double bond is. So these are unsaturated lipids. What do unsaturated lipids mean in terms of physical characteristics? They mean liquid at room temperature. Just remember that, right? This kinked shape means they don't pack together as well, and so we get a more liquid fat as opposed to a more solid fat, so more oily as opposed to more fatty. You've all heard of omega-3 fatty acids. I think I'll mention those later on. They're associated in some studies with some positive health benefits. Um, okay, cholesterol, although present at a very low percentage, uh, is a percentage that is high for our diet in terms of our dietary needs. I'll come back to that again. So, egg yolk contents fats and proteins that are associated with fats. Nutrition, right? So I just mentioned this. The recommended daily intake is about 300 milligrams. That is more or less what you can get out of a single egg yolk. Again, depending on what grade and class of egg you're talking about. Of course, high cholesterol intake is associated with cardiovascular disease. Uptake of dietary cholesterol varies dramatically among individuals, however, and so eating foods that are high in cholesterol, while generally considered a good idea, are not are actually a much more complicated story. And so genetic variations between individuals can impact the extent to which you might take up cholesterol and um, and therefore your risk for those cardiovascular diseases. So not we don't necessarily panic, but we monitor our cholesterol intake and our blood cholesterol levels. Okay, yolk nutrition continued. Saturated fat, RDI for saturated fats is 20 grams. That we can find in about a fifth of an egg yolk. Okay, so you are getting a lot of fat in a single egg, more than you're requiring for your recommended daily allotment. Saturated fats are also linked to atherosclerosis, hardening of the arteries, and diets with lots of saturated fats are actually associated with an elevated cholesterol uptake. So there's some complicated interactions going on here. On the other, unsaturated fats, on the other hand, we can consume significantly larger quantities of, um, and this has in part to do with the fact that those omega 3s, unsaturated fats, have some health benefits. So those have been found in some studies to lower blood pressure, which is a good thing if you have high blood pressure, to lower serum triglyceride levels, and to reduce risks of cardiovascular disease. LDLs, low density lipoproteins, I mentioned those a minute ago. Uh, I'm mentioning these just so we can think about why cholesterol is a positive or negative thing. Obviously, cholesterol is an important part of all of our cell membranes, so we need cholesterol, but not very much. LDLs, these are the so-called associated with the so-called um, bad cholesterol. They have low density, that is to say, lots of fats. We know that oil floats on top of water, has a lower density. So a low density lipoprotein is one that has a higher proportion of lipid relative to the protein composition. So delivering that cholesterol, loaded with cholesterol, taking it out to the tissues, that's bad, or associated with high LDL to HDL ratio, associated with the development of heart disease. HDLs, or high density lipoproteins, on the other hand, have a higher density, more protein, less lipid, and they're delivering cholesterol from the tissues to the liver. That can be a good thing. So there's a short story on LDL HDL levels. Okay, we're about to turn to a discussion of cooking with eggs. So this and other cooking methods hinge on the unfolding and aggregation of proteins. Your book uses the word coagulation quite frequently, and instead of aggregation. I will use those terms interchangeably, but basically they mean one molecule of protein associating with another molecule of protein or many other molecules of protein, and that big association eventually becoming insoluble and falling out of solution and forming a solid mass or gel. Let's remind ourselves, proteins bury their oily side chains in their cores, far away from water. This is a slide that I showed you in a previous lecture. On the left here, we see a protein, mostly polar side chains in red, exposed to water. Now I've taken a molecular knife and sliced it in half and separated them. Now we're looking at the nonpolar core, where all of those blue residues are buried away from solvent. Okay, but stresses cause proteins to unfold and expose all of those hydrophobic, oily side chains. What kind of stresses? Well, a whole slew of different stresses. There's mechanical, as I mentioned before. Whipping egg white, for example, can physically strain those proteins and cause them to unfold. Elevated temperatures, and here we're talking about 140 to 180 degrees Fahrenheit, can cause molecules to unfold. As a digression here, this really depends on where the proteins derive from. 140, 180 degrees will unfold proteins that derive from organisms that live in temperate environments, so-called mesophiles. We're mesophiles, but more typically we'd be referring to bacteria, mesophilic bacteria living around body temperature, for example, as opposed to thermophiles, which exist at elevated temperatures, and of course their proteins are not going to denature or unfold at 140 or 180 degrees. Okay, otherwise, chemical denaturations. There's a whole variety of chemical compounds that can force protein molecules to unfold in a variety of ways. Urea is one of these. I think a high school biology experiment that people do is to take one of these dissecting frogs and dunk them in a concentrated urea solution and watch them dissolve. So you can denature an entire organism with some molecules. Organic solvents are also good at denaturing proteins, and I gave you a demonstration of this on our Facebook lab activity page. So we unfold proteins in a variety of ways. That exposes hydrophobic surface area to water, which is a bad thing. What happens when we expose those oily surfaces is that they glom onto one another. One protein that normally associates with perhaps no other proteins now is associating in a random way with everybody else in solution. That again causes the formation of a long-range structure involving lots of different protein molecules, and that results in precipitation. Precipitation is when we form a solid mass from what was a soluble, dissolved mass. Finally, I'm going to mention salts. They can have a variety of effects on proteins, and your book can be confusing sometimes, and I hope that the next few sentences I say aren't terribly confusing as well. Salts are charged particles. Sodium chloride solid dissolves in water into positively charged sodium ions and negatively charged chloride ions. These charges interact with the charges on the surfaces of proteins. Shielding those charges can be a good thing. It can prevent aggregation. Sometimes two different protein molecules will have opposite charges and they'll be attracted to each other and bind together, and that could lead to an aggregation event. So salt will shield those charges from one another. The proteins will stay in solution. On the other hand, salts can drive aggregation. Again, by shielding those charges, if those charges happen to be like, then they would be repelling the proteins from one another. And by shielding them, you now remove that repulsion, and so perhaps hydrophobic patches on the surfaces of those proteins are free to interact and then, again, drive aggregation. So salt can be complicated, and we have to think about its effects in individual circumstances. In any case, once again, the unfolding and aggregation of proteins is what much of cooking is all about.